Alright, so I figured I'd make you guys a quick video showing some review problems from Chapter 6 and 7. We do have a Chapter 6 and 7 test coming up pretty soon. I've had a few questions, so I figured I'd work a few problems. Now, actually, the problems I have here on the screen are all out of the Chapter 7 homework set, but in the Chapter 7 homework set, I have a few problems that basically compare Chapter 6 questions to Chapter 7 questions. Now, in Chapter 6, we started talking about continuous distributions, and specifically the normal distribution. Turns out there's lots of natural phenomena that can be explored because they follow a normal distribution. Okay, so let's take a look at this first question here, top left. It says the distribution of all registered nurses' salaries on the Treasure Coast is known to be normally distributed with a mean of $58,150 and a standard deviation of $525. Use this information to determine the following two probabilities. Round your solutions to 4 decimal place if necessary. Now, the first question says, find the probability that a single randomly selected nurse's salary is greater than $57,998. Now, what you need to recognize there is, the reason I have that word single emphasized is that means we're working basically in Chapter 6. Chapter 6, every question we were talking about population distributions. We were asking questions like, what's the probability that we select a single observation and that single observation is greater than some value or less than some value or maybe between two values? Okay? Chapter 6 is all about populations and what's the probability that a single item is greater than, less than, or between. Okay? Now, the second question here is find the probability that a random sample of 64 nurses has a mean salary greater than $57,998. So if you were just glancing here, you might think that both these questions are asking the exact same thing. But you have to read carefully, and that's kind of the point of the question, is that the first question is a single observation, and the second question is a sample. Okay, you're talking about a sample in the second question. Now, when you go to take the test, nothing's going to tell you, hey, this is a Chapter 6 question or this is a Chapter 7 question. But if you can do the stuff in Chapter 6, then you can do the stuff in Chapter 7, as long as you notice that we slightly tweak the formulas a little bit. But basically, we're doing the same thing, just in a little bit of a different setting. So let's do the Chapter 6 question first. Again, this question up here, this is a Chapter 6 question. Chapter 6. We did tons of questions just like that in Chapter 6. Basically, we want to do, like the question says, probability that X, where X represents a single nursing salary, a registered nurse's salary on the Treasure Coast, we want to find the probability that's greater than $57,998. Okay? Now, we can either use our calculator, or we can use the table. Now, I'll solve using the table first, by hand, and then we'll check ourselves using the calculator. So if we're going to do this by hand, we know we need to use our standard normal table. That is, we need to standardize and convert that X value, that dollar figure, to a Z value. So this is dollars are the units right now, $57,000, almost $58,000. Clearly, we can't go to our Z chart right now because, first of all, that's not a Z value, it's a dollar figure. But even if you just recognize it's a number that's not even close to being on our chart, so we have to go and convert this to a Z value. Now, what's our Chapter 6 Z value formula? In Chapter 6, our Z value formula was Z equals X minus mu over sigma. Okay, that is, you take an observation, subtract off the mean, and divide by the standard deviation. So for this first problem, we're talking about the observation 57,998. We subtract off the mean, which is up here. We should probably jot that information down. It's always good to write down the important information. Mu is equal to 58,150. We should probably jot down sigma too. Sigma is the population standard deviation, which is 525. Okay, so now we're going to go back. We're subtracting off the mean, so 58,150. And we're going to divide by the standard deviation, which is 525. Okay, so that's going to give us a z value. Let's see, I'm going to do the calculations off the side for just a moment, and then I'll come back and show us how to do it completely on the calculator. So we're doing 57,998 minus 58,150 divided by 525, and that gives us a z value, and rounded to two places, negative 0. Let's see, the two places is going to be 30. So we have a z value of negative 0.3. Okay, so negative 0.3. Now, once we have a z value, we can simply go to the chart and solve. Now, there are two ways to solve a greater than probability in terms of z. Okay, we can either solve by basically looking up the z value, negative 0.3, and then subtracting that value from 1, or we can look up the opposite of this z value. Now, why is that the case? Because if we draw a picture of a normal curve, we are trying to find the probability that z is greater than negative 0.3. So if 0 is right in the middle, z equals 0, negative 0.3 is just barely there to the left. Okay? I mean, it should be even closer. It's just barely to the left there. Now, we want a greater than probability, so we're going to look to the right, find the area to the right, like so. But we know that our standard normal table always gives us area to the left. So if we go to the standard normal table and look up z equals negative 0.3, the table is going to give us the area to the left, this bit of blank region over here, not the shaded region that we want. So we can do one of two things, like I mentioned. Either we can look up negative 0.3 and then subtract that value from 1, which is doing this. Because if we look up negative 0.3, then we're going to get the area to the left, and then subtract that area, that value from 1. Or the quicker way is if you look up the opposite of negative 0.3, which would be like find the probability. Oh, and I messed up. Let me fix that really fast. I said x. That should be a z value. Probability that z goes there. So then I need to fix this too. That z, so we can look at the opposite of negative 0.3, which is positive 0.3. So z is less than 0.3 positive. Now, why does that work? That's because of symmetry. Basically, if you look at positive 0.3 instead of negative 0.3, and then look at the area to the left, the yellow shaded region and the red shaded region, or the orange shaded region, will be equal because of symmetry. So either of those two methods will get you the exact same answer. Here, give me just a moment, and I will bring up our z table. All right, so we're looking for positive 0.3 and then subtracting, actually just looking at positive 0.3. So let's see, positive 0.3, so this is a value right here, so 0.67, 6179, so 6179 should be our solution. (6179). Or, you know, if you're going to look up negative 0.3, we should get a value. Subtract that from 1, and we should also get 0.6719. So let's see. If we do this way, if we do this method, that'll be 1 minus. Now let's look up negative 0.3. Going to the negative z value side, negative 0.3 is 0.3821. So we're going to do 1 minus 0.38. And if we subtract 1 minus 0.3821, we do end up getting precisely 0.6179. Okay. Now, what's the interpretation there? The interpretation there is if we randomly select a single nurse, a single observation out of all registered nurses on the Treasure Coast, and say, hey, what's your salary? There is a 0.6719 probability that the salary of that nurse will be greater than $57,998. Okay? You're talking about a single observation, a single nurse out of all the nurses on the Treasure Coast, which is our population. Now, where we move into Chapter 7 is when we start talking about a sample. So the second question says, find the probability that a random sample of 64 nurses has a mean salary greater than $57,998. Now, where this changes, here I'll write over what we've been doing. Where things change, I'll just do a little bit of erasing and show how it's basically the same steps. Is that we go over here, instead of having an X there, because we're no longer talking about a single observation, now we're talking about an X bar because we're talking about the mean of a sample of 64. So we're not talking about talking to a single registered nurse. We're going to talk to 64 randomly selected nurses, ask them all what their salary is, and then calculate the average of that salary, and we're going to ask what's the probability that that average salary is bigger than $57,998. Okay, so where things change is that symbol has to change because we're talking about a sample now, but we still need to convert that to a z-value. Now, the z-value is going to change, so I'm erasing all these z-values that we calculated last time, because our z-value formula had to be tweaked when you're talking about a sample. Okay, so we have to look at our z-value formula for Chapter 7 now. So let's get rid of this. And I'll jot down our Chapter 7 z-value formula. We'll see how it's a little bit different than Chapter 6. The numerator, in fact, is the same. So in Chapter 7, our z-value formula is z equals x bar, so not x bar, but it's still minus mu, over the standard error, sigma sub x bar. Now, remember that sigma sub x bar has a formula. Sigma sub x bar equals sigma over the square root of sample size. Okay, so now we have to calculate our z value using the Chapter 7 z value formula because we're working with a sample. Anytime you're working with a sample and talking about a sample mean, a question about a sample mean, you have to use this tweaked Chapter 7 z value formula. Now we're going to have another z value formula here in just a minute for proportions, but when you're talking about a sample mean, this is your go-to. Now, so if we substitute in, let's see, z equals, the numerator is precisely the same. It's x bar, 57,998, minus the mean, which was the 58,150, divided by, not the standard deviation, the standard error. It's also called SEM for short, the standard error of the mean. And its formula is the standard deviation, which is 525, over the square root of sample size, which was 64. Now, just be careful when you're putting this in your calculator. Put parentheses around the numerator and denominator. And let's see what we end up getting here. 57,998 minus 58,150 divided by 525 over the square root of 64, so it's 525 over 8. And we end up getting a z value this time of negative 2.32. Negative 2.32. So last time our z value was negative 0.3. This time it's negative 2.32. Why is that the case? Because our standard error, our standard deviation of the sampling distribution, is much smaller. Anytime you're working with a sampling distribution, because you're dividing the standard deviation by the square root of sample size, the standard deviation is going to be always smaller for any sample size bigger than 1, essentially. Okay, so we go back to our statement over here, and now we're looking at z is greater than negative 2.32, which then we can solve since it's a greater than probability by either looking up negative 2.32 in our table and then subtracting that value from 1, or we can look up the opposite of negative 2.32, which is positive 2.32. Either one will work. Now let's erase that old picture, and we'll draw a new picture. You always want to draw a diagram to help yourself solve these. It's easier to visualize what's going on here. Okay, so we have a 0 right in the middle. Now this time we're looking at z is greater than negative 2.32. Now that's going to be over here, negative 2.32. And we're looking to the right. So we want to shade to the right. Now notice, always check to see, ask yourself, what should my answer look like? I'm shading most of the curve here. So if I had to guess, I would say I'm probably shading, 90, 95% or so of the curve. The total area is 1. So our answer should be somewhere in the ballpark of, say, 90 or 95, percent, or 0.9 or 0.95%. If you get your answer and your answer is 10% or 0.1, you made a mistake somewhere. So that's what we draw a picture just to make sure that we are getting a reasonable answer. Now, how let's go and get the answer. We can go to our chart. So let's look up. Let's first solve doing this method, 1 minus the probability that z is less than negative 2.32. So we're going to look up negative 2.32. So negative 2.32. It gives us that value. So 0.0102. 0102. Okay, so 1 minus 0.0102. So that gives us 9898. Sorry about that. Equals 0.9898. So I said 995. I was actually off a little bit. But that still seems reasonable considering our little diagram right here. Now, we can get the exact same answer by looking up the opposite of negative 2.32, which is positive 2.32. Let's do that really fast. If we look up positive 2.32, 2.32, yep, there we go. 9898, precisely the exact same solution. Again, why is that true? That's true because of symmetry. Because of the curve being symmetric, if you go over here and you look at positive 2.32, but instead you look to the left, then the pink shaded region and the blue shaded region will be precisely the same shape, and they'll have the exact same area. So again, 0.9898. Okay. Now, why is the answer so much different than it was before? Okay. The answer is so much different because when you're talking about a single observation, that single observation, that chapter 6 question, you could pick an outlier. You're only picking one person. When you pick one person randomly, you're usually going to pick somebody close to the mean. So you usually pick somebody that has a salary close to $58,150. But you could, occasionally pick somebody with a salary of $65,000 or $70,000 or $100,000. But usually you'll pick somebody close to the mean because that's what it means to be average. But when you have a sample of 64, if you think about it, think to yourself, okay, if I pick 64 people, if every one of those observations is usually close to the average, not always, but usually, you'll have to have a couple outliers. But if you have 64 and you average those 64 values that are generally close to the mean, well, then the average is going to be pretty close to the mean. Okay? When you're talking about $57,998 or more, basically that's a little bit lower than average, or everything above. So that's why our answer is 0.9898, because when you ask yourself what's the probability of being having a little bit below average salary, an average salary, or above, that's pretty much everybody. And that's why you have the large answer here close to 1. So again, that was a chapter 7 question because it was a sample. So anytime you see the word sample and you're working in chapter 6 and 7, you have to be in chapter 7 because 7's all about sampling distributions. Chapter 6, we never use the word sample because it was all about population distributions. Now, let's look at this other chapter 7 question real fast. This is just straight up a chapter 7 question. And let's see what it says. It says the mean weight of all Goliath grouper caught on the Treasure Coast is 409 pounds with a standard deviation of 64 pounds. Suppose a random sample of 51 Goliath grouper from the Treasure Coast are caught and weighed. Determine the probability that the average weight of the sample of 51 Goliath grouper is within 15 pounds of the average weight of all Goliath grouper caught on the Treasure Coast. Okay, so basically it's saying what's the probability that you're either 15 pounds above average, 15 pounds below average, or somewhere in between. So if we write that out in symbols, this word within means exactly what I just said, above, below, or in between. So we want to do the probability that x bar, the sample average, is between, okay, well, what's the average here? The average is 409 pounds. So there is mu. By the way, there's sigma right there. Sigma is the population standard deviation. Mu is the population mean. So if your 409 pounds is the mean, well, what's 409 plus 15? Actually, let's do minus 15 first. 409 minus 15 is 394 pounds. So 394 pounds. And if you take 409 and add 15, you get 424. So being within 15 pounds of the mean indicates that we need to say 409 plus 15, which gives us 424, or 409 minus 15, which gives us 394. So we're asking the question, what's the probability that we go catch what was it? Our sample size here is 51. What's the probability that we go catch 51 Goliath grouper, and the average weight of those 51 is somewhere between 394 and 424? I want you to think about this. This kind of is like what I was talking about in the last question. We're saying, what's the probability we get 51 fish? They either weigh a little bit above average, a little bit below average, or somewhere between. To me, that says probably a pretty good probability. Now, 15 pounds, the standard deviation is 64 pounds. So, we'll have to calculate a z value to figure out exactly how, what our answer is going to be. But I imagine our answer is going to be, a fairly good number. So let's see. Our strategy, once we have our probability statement, is to convert to z values and then use our chart. And then I'll show you how to do it on your calculator after that. So probability, we want z is between two values. Because as soon as we get z between two values, then we can just go to our chart and solve. So we need to convert 394 to a z value and 424 to a z value using our Chapter 7 z-value formula. So let's do that down here. Let's do the first one. Is going to be 394 x bar minus the mean, which is 409, over the SEM, the standard error, which is sigma 64, over the square root of sample size 51. Okay? Now, real fast, I'm going to punch that into a calculator. Make sure to put parentheses around your numerator and your denominator, or else your calculator might not do what you're thinking it does. So this gives me a z value of negative 1.67. Now, really, if you're paying attention, you don't really have to worry about calculating another z value. What do you imagine is going to happen? Watch how the numerator is here is just negative 15, because that's how we got this 394. We subtracted 15 from 409 and got 394. When we do the other z value, which is going to be x bar 424 minus the mean 409, the numerator is going to be positive 15 instead of negative 15. The denominator is still exactly the same, and you're going to get 1.67. Here, I'll punch in my calculator just to make sure I didn't make a mistake on the first one. But as long as the first one was correct, and it indeed was negative 1.67, then the second calculation has to be positive 1.67, just because of symmetry here. So 424 minus 409 divided by, put parentheses around your numerator and denominator, 64 divided by the square root of 51, and yep, we get positive 1.67. Okay, so positive 1.67. So going over here now, we want to find the probability that z is between negative 1.67 and positive 1.67. This, once we convert to a z value, is precisely a Chapter 6 question. That's why you always hear me say, it's really important that you know how to do Chapter 6, population distributions. And if you really master that, Chapter 7 is not so bad, as long as you pay attention to how the differences between working with samples and working with populations. So remember how we do a between type probability. we first look up the larger number, 1.67. So we're doing this. The probability that z is less than 1.67. That's what we're doing when we look up the bigger number. You look up the smaller number, the negative 1.67. When we do that, we're looking at that z is less than negative 1.67. And then you subtract. Now, why does that work? Here, I'll draw us a quick picture. Of course, 0 is right in the middle. Positive 1.67 is maybe about right there. Negative 1.67 is about right there. If you look up positive 1.67, we get all of this shaded area. Everything to the left. That's what the chart does for you. Everything to the left. Now, clearly, that's too much because we just want the region between positive 1.67 and negative 1.67. But when I go and look up negative 1.67, I get all the area to the left of negative 1.67, which is the yellow. Basically, the yellow was the excess that I wanted to get rid of. And when I look up negative 1.67, what I'm left with, and I subtract, what I'm left with is just the original, which is this region here, which is what I wanted all along. So that's why this method works, because of the way our chart is set up. It always gives area to the left. Now, let's go to our chart real fast. Look at positive 1.67 first. So positive 1.67, the 1.6 row, 0.7 column, 9525. So 9525 minus, now we need to look up negative 1.67. So negative 1.6, that row, and the 7 column looks like 0.475. 0.475. So subtract off 0.0475. When we do that, 0.9525 minus 0.0475, we get 0.905. 0.905. So, yeah, I mean, looking at my picture here, negative 1.67 is actually a little bit further to the left. Positive 1.67 is a little bit further to the negative 1.67 is a little bit further to the left. Positive 1.67 is a little bit further to the right. This is not drawn to scale. I should have done a little better job drawing that. But this answer makes sense conceptually. Okay, that we're looking for our average of the 51 fish to be a little bit either a little bit above average, a little bit below average, or somewhere in between. So yeah, that makes sense. Now also think about this probability statement right here. We should also think that we have a good idea of what the answer is going to be due to the empirical rule, because we know that the empirical rule says that the area within one standard deviation is about 68.44%, or 0.6844, if you're talking about a raw number. And the area within two standard deviations is about 95%. So it's not a linear relationship, so that's why we get the 0.9. But we know that our answer should be closer to 0.9544 than 0.68, and we end up getting the 0.9. Now, let's check ourselves using a calculator. So let me pull it up real fast. You can do both of these using a calculator. Let's go back. Let's do the grouper one first, since we were just talking about it. Then we'll go back and check our other solution. Now, again, you don't have to have a calculator to do this class. I just did both solutions by hand. I talked. I'm a little long-winded, so they take a little bit of time when I'm explaining every step. That being said, if you're not talking about it, you can do these problems in a few minutes each. Maybe 3 or 4 minutes each. With a calculator, you can cut that down to a few seconds as long as you're careful. Now, actually, I said let's do the grouper first. Let's do the nursing salary question first, because I want to show you how to do Chapter 6 question first. Then I'll show you how it's different than a Chapter 7 question. Okay, so what you have to do is go to the second VARs, the distribution menu. So see there it says DISTR, distributions, but you have to hit the second button, the blue button, to get there. And what we want is the normal CDF. So hit normal CDF. Now, if you have one of the newer calculators, you get a menu option right now. Here, there's no menu to work with. Some of the newer ones do have a menu. You're inputting the same information either way. So if you don't have a menu, if you have a TI-84, one of these editions, the Silver Edition Plus, or say you have a TI-83, will be the exact same way. You have to type in here. I'll put the syntax down here. The syntax is normal CDF. It's lower, comma, upper, comma, mu, comma, sigma. Okay, that's the syntax you have to know. So what's our lower? Okay, we can actually go back to our original statement right here and look at the probability so the probability here that X is bigger than 57,998. So we're talking about a nursing salary being at least 57,998. And, well, we don't have an upper limit. It just says bigger than. So technically, $1 million would be bigger than. $10 million would be bigger than $1 billion. Like, there is no upper limit. We're just saying what's the probability that's bigger than that 57,998 figure. So what we need to do, we want to say positive infinity, because that's what we were really saying here. For any number that's bigger than that 57,998 figure. No, we can't type in infinity, so we just make an approximation. It's not really an approximation. We just say a big number. So I just put a bunch of 9s there. That's a big number. Okay, that'll take the place of infinity for us, positive infinity. Okay, and then we do mu. Okay, so mu was 58,150, and then comma the standard deviation, which was 525. You don't have to close the parenthesis, but it looks nice if you do. Hit enter, and there we go. Now, I don't remember what our answer was. I foolishly erased it. Was that it? I guess you'll know because you can rewind it. I can't check it right now, but that's what the calculator is giving us. Now, you have to keep this in mind. The calculator does not have to round at these intermediate steps. So almost always, the calculator answer is going to be a little bit different than the by hand answer. That's no big deal. It just happens. Okay. The homework is set up such that there's tolerance built in the questions, and you get credit for doing it on a calculator, or by hand you still get credit. Okay, so that's the answer. I hope it syncs up with our original answer for this first question from Chapter 6. Now, how does it differ from Chapter 7? The syntax is still the same, but you have to be careful about what the standard deviation is. Because if you're working in Chapter 7, you have to use the standard deviation of the sampling distribution, which is sigma over the square root of n. Okay, so go back second vars to give you a distribution menu. Normal CDF, hit enter, and now our upper and lower are precisely the same. The lowest value we're talking about is 57,998. All the way up to positive infinity. We'll just substitute a bunch of 9s instead. The mean, if you remember, the mean of the sampling distribution is always equal to the mean of the population, which is 58,150. But the standard deviation is different. It's this SEM, the standard error, which is sigma 525 divided by the square root. Let's see, square root. Now all of a sudden my brain's blanking now that I'm doing this on a different calculator. Divided by the square root of sample size, which was 64. I guess I could have just typed in 8 since that is the square root of 64. Hit enter, and now we can actually check ourselves. 9897. So okay, notice we always round probabilities to 4 places. 9897 is what the calculator tells us. Our by hand solution was 9898. Again, that 4th place being off by 1, let's see, 10, 100,000. Being off by 1 10,000th is no big deal at all. Okay, that just happens. The calculator is actually the better answer, but it's no big deal that our by hand answer was slightly different. That's almost always going to happen. Not always, but a lot of times. Okay, let's then check ourselves over here. Again, this is a Chapter 7 question because it was all about a sample of 51 grouper. So we need to make sure to use the standard error whenever we type in the syntax like I have here in yellow. Second vars, go down to second option, normal CDF. So now we actually do have a finite lower and upper. So 394, comma, 424, comma, the mean, which was 409 pounds. But I got to make sure to type in not sigma, but the standard deviation of the sampling distribution, which is sigma over the square root of sample size. So 64 is the sigma population standard deviation divided by the square root of sample size, and the sample size was 51. 9058. Okay, so notice that is a little different, 905. And again, that's 8 10,000ths different. So our answer by hand, has a 0 here. That's just how it worked out when we did it by hand. But, it's a little bit different. But, 8 10,000ths is nothing to worry about. That's completely fine. Okay. So just always keep in mind that if you usually when you're doing it by hand, your answer will be slightly different, but it's not a big deal. Okay. I guess that really wraps up these 2 examples. Again, the first compared Chapter 6 to Chapter 7, so that was a little bit of review of Chapter 6. We did a few other things in Chapter 6, but this is what we spent most of our time in Chapter 6 was doing stuff just like this. And then, we transitioned here to Chapter 7. So if you have any more questions, feel free to email me and or post on Blackboard, and I'll be more than happy to help you out. And yeah, we'll see you soon.